As Wade mentioned, I'm Reza Asiyabi, and I'm currently a postdoctoral researcher at the University of Edinburgh and UK National Centre for Earth Observation, or NCO. I generally work in developing machine learning and AI algorithms in general for mostly Earth observation applications. The topic that today I want to talk to you about is complex value deep learning for synthetic aperture radar, or SAR data, which is mostly done during my PhD when I was a Marie Curie early stage researcher fellow with Menelaos project at University Polytechnic of Bucharest in Romania and University of Siegen in Germany. So I will start the presentation. Today, I will give a very brief background of why do we need complex valued networks, what they are good for, and what they are capable of. And I will show their I will show them in three different architectures, very simple architectures, in different case studies to test these models. And finally, I will talk very briefly, maybe 5 to 10 minutes, about the work that I'm doing here in Edinburgh. So let's start with the theoretical background. I don't know how familiar you are with SAR data, but just very briefly, SAR is an active Earth observation sensor that emits microwave signals and receives the backscattered signal from the Earth's surface. And in this way, it provides very rich and unique source of information for monitoring the Earth. But it comes with its own challenges. SAR data is very intricate and more challenging to process and work with than, let's say, optical remote sensing data. As it's shown in the illustration here, SAR data has a side-looking geometry which introduces different distortion metrics, geometric distortions, like foreshortening and shadowing, etc. It also has a spectral effect, which is a noise-like effect in SAR data, which we have to also deal with, and many other challenges. But the two challenges that we are more interested in this work is that SAR data has a very complex data model with inherent adversarial samples that we need to model. And beside that, SAR data are in complex domain by nature, meaning that the data has amplitude and phase information, or the real and imaginary components. Just to emphasize a little bit more on what I mean by the more complex data model than just normal vision data. I have some examples of the inherent adversarial samples here. It's showing images like for SAR data and optical data from the same bridges. In here, for example, in the first row, in the optical data, we can see that there is just one bridge. And with a very good vision model, we can detect this bridge. But on the SAR data, we can see, I don't know, maybe 3 or 4 parallel bridges. And the most accurate vision model will detect 3 parallel bridges in here, which, well, it's correct in vision side, but it's not really true. And it happens because of the multipath scattering in SAR data. So when we say that the networks has to be able to learn this data model of this complex data, it means that they have to detect these kind of patterns. They have to detect this kind of phenomena in SAR data and be able to deal with it. So just to state our problem, we mentioned that SAR data is very unique and we needed to monitor our Earth, but they are very complex, and we need capable models to model this data. And what's the most capable methods for complex systems? Well, definitely deep learning and AI. But there's another problem with that, and is the complex valued nature of SAR data. Most of the developed deep learning models are in real valued, and the to-go approach to apply these real valued models on SAR data was to just forget about the phase information and apply it to just amplitude information from SAR data. And it's okay for some applications, it works perfectly well. But in some applications, like when we are using raw SAR data or in interferometric SAR applications, we need the phase information, so we cannot just disregard it. So in this study, we develop complex valued architectures and we test how capable they are to understand the complex data model of SAR and how they can preserve the original properties, the complex coherency, and the physical attributes of this data. In complex valued networks, all the operators, all the layers are in complex values. So for example, in convolutional operation, which is a very common, very useful operation in defining deep learning models, is the one showing on the first line of this equation. All the parameters and the variables in this equation are in complex domain, having real and imaginary components. So if we replace them, the multiplication between the weights and the input feature maps will become these two lines here. More computationally intense, but it is visible. And we can do the same for, well, not all, but almost all other operations that we need to define deep learning models. And we can, in this way, create complex valued operators and define complex valued networks. And once we have the complex valued networks, we will need complex valued backpropagations, BP, to train these models. And thanks to the vertical calculus that extended the complex derivative to even non-holomorphic functions, we can take the complex derivative from these layers, and we can compute the complex backpropagation in the similar way that we would do in real values by taking the derivative of the loss function with respect to the parameters that we are computing the correction term for. In complex values, also, we would do the same, but the parameter has real and imaginary components, so we need to take the complex derivative, and we have to use complex chain rule to compute this derivative. Again, more computational intense, but feasible, and in this way, we can train complex valued networks as well. And so once we have these complex values, let's go to the application and see some applications and how useful they are. Well, before that, the first problem that we faced when we started this work was the data set. Because most of the data sets, the annotated SAR data sets that are available, they use detected or real valued SAR data. So we had to create our own data set. We created this data set. We call it S1 SLC CVDL data set. I regret naming it this. It's very not a catchy name, but it is very self-explanatory. This data set is from Sentinel-1 data, single-look complex products, and we used SM or a strip map mode data, which is the highest resolution SAR data from Sentinel-1. And for annotation, we first annotated this dataset into three different general classes: vegetation and agriculture, constructed regions, and water regions. And then we further divided these classes to agriculture and forest, or in general, woodlands. For constructed regions, we divided it into four different classes of high-density urban, high-rise buildings, low-density urban and industrial regions, and water regions stayed the same, just the water bodies. And we use this data, which is, by the way, available on IEEE Dataport if you want to use complex valued data. We use this data set throughout this presentation, unless in one or two case studies that I will mention. And as the first architecture, we have a very simple architecture consisting of a convolutional encoder with a convolutional decoder head and a convolutional classification head, and nothing fancy, just a very simple convolutional network. And we implement a complex valued version of this model, and we use it in different case studies that I will walk you through. In the first case study, we just simply wanted to give the complex valued data from the dataset that I mentioned. Well, what I forgot to mention is that dataset had two polarizations, HH and HV, which is the polarization that we get from Sentinel-1. So we use both polarizations, and we give it as the input to the model, and we classify it. The three-class classification is not very intuitive because it's very simple classification. A very simple model would perform well on it too. But the 7-class classification is more difficult and more intuitive. With just 2 polarizations as the input, we get about 91% classification accuracy. In the next step, we wanted to add some physics-aware features to this network. So by physics-aware features, we mean the star aperture images. If you are not from star background and you don't know what star aperture images are, I have a figure that I can show you later in the appendix to explain it better, but just very briefly, star aperture is a signal processing techniques that virtually divides the synthetic aperture of star into multiple sections and generates an image from each section of this synthetic aperture. And in here, for each polarization, we divided the synthetic aperture to 3 different star apertures and generated 3 different images. So in general, 8 input features to the model, to the complex valued model. And the classification accuracy increased by about 3% and we reached about 93-94% classification accuracy. And in the next step, in order to compare it with the real valued network, we implemented a real valued version of the same architecture, and we classified the same data, the star and star aperture images, but just the amplitude of the same data. And the classification accuracy dropped to about 79%, which is more or less 15% lower than the classification accuracy that we had with the complex valued model. But complex valued network has 2 times more learnable parameters than the real valued version model. So it is expected to perform much better. It's nothing surprising here. So in the next step, we compare it with a more complex real valued architecture with more trainable parameters than the complex valued network that we had, which is the high resolution network or HRNet. At the time, it was one of the very good models for classification, so that's why we chose this one. And we use this with real value, the amplitude of the data for star and star apertures to classify it, and the classification accuracy gets to about 90-91% classification, which is very close to the complex valued network when it had just the star data, not the star aperture information. And it's still about 3% lower than the complex valued network, despite having more parameters. The HRNet I mentioned has more trainable parameters than the complex valued network that we implemented here. And well, we saw that it's working reasonably well for classification of star data. So let's, in the next step, we wanted to test how good it is, how capable it is in learning the complex data model of star. So we used the reconstruction head of the architecture and we reconstructed the input star data. We are showing the input star data in the first column. The second column is the reconstructed star data and the coherence between these two. I'm sorry. The coherence between these two in the third column. Sorry. And well, we get the average coherence of about 94%, which is reasonable, but a good vision model would do the same, even better by just matching a pixel to pixel. So we needed a more accurate and more difficult test for this. So what we did was to get the star apertures in the same way that I mentioned from the input star data and apply the same signal processing technique to the reconstructed star data and get the star apertures from that one too and compute the coherence between these two star aperture images. And we get about 92% average coherence between them, which shows to some extent that the model is learning this complex data model and can preserve these original properties of star data. So in the next step, in order to test how well it can preserve the physical information and physical attributes that there is in star data, we did this test. At the time, one of my colleagues was working on estimating ocean surface currents from SAR data, from interferometric wide swath mode or IWSAR data, which is a lower resolution SAR data from Sentinel-1. So in this experiment, we once estimated the ocean surface currents from the original IWSR data that in the same way that he was doing. In the next step, we fine-tuned our model with some IWSR data from Sentinel-1, and then reconstructed this SAR data using this model and estimated the ocean surface current from the reconstructed SAR data and compared the results. The first row is the estimated Doppler centroid, which is then used to estimate the ocean surface currents from the SAR data. And by comparing them, we get about 97% coherence between them, which shows to some extent that this model, by reconstructing it in this process of reconstructing the SAR data, it is preserving the physical attributes, physical information that exists in SAR data. And if we do it by, if we do it just on the amplitude, we cannot compute this because we need the phase information for this. But even if we use amplitude and phase as separate bands or channels in the real valued network and reconstruct them and then put them together as a complex valued network and try to do the same, we will not be able to get good estimates of the ocean surface current because the correlation between the amplitude and phase would be lost. So in the next step after testing this, we wanted to look more into how complex valued and real valued networks compare in terms of classification in more details. So we use a very simple CNN architecture. We implement a complex valued and real valued version of this architecture, and we use it to classify the SAR data, which I'm showing the Pauli RGB composite of it in here with the ground truth map that we had for this data with 15 different classes. Most of them are from agricultural crops. And in the bottom row, we are showing the classification map from the complex valued and the real valued CNN. And just by visually comparing this classified maps, we can see the better and smoother classification by complex valued network. For example, if we compare this small island with forest cover in the ground truth map, in complex valued map, we have more smoother classification, more accurate classification, and the same goes for most of the other classes as well. And in here we have the classification accuracies, but I believe I have the accuracies in the next slide. Yes. Well, complex valued network gets about more than 95% accuracy, which is more than 5% higher overall accuracy than the real valued network, and higher classification accuracy for almost all the classes except for one or two. But again, the same question comes here, that complex valued network has 2 times more trainable parameters than the real valued network. So it is expected to perform better. So in the next test, we wanted to compare the convergence and how the training size affects this, the performance of these networks. So we get this plot on the left side, which is a very cluttered plot, but we won't dig into all the information in it. Just to understand this, in the legend, CV stands for complex valued and RV stands for real valued, and the percentage in front of them is the percentage of the labeled data that we use for training set. And we plotted the classification accuracy of each of these networks in across different epochs of training until 100 epochs. And just to compare one, if we get the real valued network with 50% training set size, the biggest training set size that we have, which is this darker green shade, it gets to about more than 94% accuracy after 70 epoch. And classification accuracy is kind of plateaus after that, and it doesn't increase after that. And if we get the lowest training set size, just 5% with complex valued network, which is the brighter blue shade, I believe it should be this one, we get to almost the same classification accuracy, slightly lower 94% after 100 epochs. And even with 10% training set size, we get to higher classification accuracies, even sooner, with about 30 to 40 epochs with the complex valued network. With complex valued network with 50% training set size, we get to over 98% classification accuracy. So, for example, if we put a target overall accuracy of, let's say, 90%, the complex valued network would require about 17 epochs to get to this accuracy, which will take about 173 seconds to train. While the real valued network, despite having like 2 times, half the number of the parameters that it has, it takes 39 epochs to get to that overall accuracy, and it needs about 192 seconds to train this. So the conclusion that we get from here is that complex valued networks utilize more information from the source data and can get to target overall accuracies faster and with less training data. And in the next step and the final application that we had for complex valued networks, we wanted to use somewhere that complex valued networks are necessary. It's not just an option if we want to use deep learning. And that's where we are working with SAR raw data. SAR raw data, if you're not familiar with it, is it's not very visually informative. It's more like a noise, and SAR sensor acquire it. And it has to go through some signal processing called focusing to generate the SAR data that is more visually informative. But this SAR raw data, in order to be transformed into the ground station from the satellites, it needs to be compressed on the SAR for a more efficient transformation. And we wanted to use these complex valued networks for compression, for data compression of SAR raw data on board the satellites. So we use the neural data compression technique, which is a technique which uses the deep learning models for data compression, and it's very effective for vision data. And the idea behind it is to have an encoder which encodes the input data to the latent features, and then we have an entropy encoder which losslessly encodes the latent features to some bit stream, which is the compressed form of the data. And in order to decompress it, we use the entropy decoder with the same model to recover the latent features, and then there is a decoder network which reconstructs the data from the latent features. And in order to train this, loss function typically has 2 terms: the rate term, which uses the Shannon cross entropy to estimate the bit rate which is required to store the compressed bit rate, compressed bit stream, and the distortion metric, which can be any distortion metric, mean square or anything that is more suitable for your data. So we use this notion, and we implement this autoencoder architecture, which consists of a complex valued encoder, which convolutional layers, and a complex valued decoder, almost the mirroring of the encoder, and lossless entropy coding. We use arithmetic encoder and decoder here at the bottleneck for lossless entropy coding of the latent features. We implemented another architecture. We improved this architecture as well with adding some residual blocks to make it deeper and more capable, and also adding a hyper network for more efficient entropy coding. But the results that I'm showing here are from the first architecture that I mentioned. So in order to train this, the input to this network was SAR raw data, as I mentioned, the noise-like data that we want to understand visually. And the output is also SAR raw data, and we train it just based on SAR raw data. But when we want to evaluate it, we applied the focusing technique, the signal processing technique that I mentioned, to the input and also the reconstructed or the output data to get the star images and compare the two products together, because we don't want to compare just the raw data with our purpose is to get accurate and more informative star data or star images that we want to work with. And we compare it with two different methods. BAQ or block adaptive quantization, which is a standard data compression technique for most of star data missions, including Sentinel-1 and TerraStar-X. And JPEG 2000, which is a common and standard data compression models. And across three different metrics, signal to quantization noise ratio, phase error, and the coherency, complex valued autoencoder based architecture performs better than those two standard models, and it's giving a better performance. And we couldn't compare it with real valued networks here because in order to be able to focus our data and get the star images, we require amplitude and phase, both real and imaginary components of it, and we cannot use real valued networks here. And we have also some images, some output images from the different models as well. We cannot visually see much difference with them because we have to zoom in and find these differences, but we can see the bit rate and SQL for each of them, which shows that the complex value of the encoder, despite having the lowest bit rate, which is like the highest compression, it has a higher SQNR, which is higher quality compared to the other two methods. And well, that was all I had to say about my PhD, but I'm not quite done yet. I will skip through this appendix because they're not very important right now. If we have any questions, we can go back to them. But before I finish, I will talk a little bit very shortly about my work here in Edinburgh. Well,
sorry, Reza. Sorry, Reza.
Yes.
Maybe it's good to first get questions from your first part and then move on to this. Is that possible?
Yeah, sure,
Okay.
no problem. Yeah, sure.
Yes.
I'm
any
happy
questions?
to answer any questions.
Any questions from Reza?
Sorry, is it possible to ask questions? Is it okay?
Yeah, please.
Sure.
Yes, please.
First of all, thank you for your great presentation. It was very informative.
Thank you.
And I wanted to know for that work that you had done with the reconstruction of the SAR data.
For the
I
compression?
think the second one.
Or data compression or the coherency?
The one before that, yeah.
Mm-hmm. Yes.
What is the input? What is the input that you're using in this network? I don't understand which. I know that you are using SLC product from Sentinel-1, but what do you extract from these SLC product to fit to the network?
SLC products themselves, just the images themselves, and
just the
also
images.
Yes, and also the saw aperture images that I mentioned here. In the beginning, we had just the SLC images, two polarization, HH and HV. And in the next step, we also included the saw aperture from each of those polarizations. So in total, 8 input features, 2 polarization, 2 SLC images, and then 3 saw apertures from each polarization. So 8 input features.
And did you use any special loss function for these complex valued network?
No. Actually, the loss function has to stay real valued. Loss function cannot be complex valued, so loss function has to stay real valued. We cannot compute the complex derivative with a complex loss function. So loss function stays the same. same. Because like for classification, well, the classification output is real valued because we have the class labels. And also for reconstruction, we want the real value to match the real value from the input data, and the imaginary part also match the imaginary part from. So we can compare both of them separately and compute the real valued loss. But except for the loss, the other parts of the network were complex valued.
Okay, thank you. And you use patches of these the bigger image, and that fed these patches to the network, right?
Yes, yes.
Did you stitch these patches back together at the end, or you just compare the patches?
Well, to do what? Because like the classification is patch level. So even if we stick the patch, like move like the patch together and get the spin, it will not tell us anything because we have one label for each patch from the data set that we have. So it's not like a pixel level classification.
Okay, I understand. I think that's it for me. Thank you.
Yeah, thank you.
Reza, I have a question. So you have customized a new neural network model to work for SAR data, especially with single complex data, and you showed the mathematical formulation that you have developed. So it seems that it works well because you showed 5% most cases classification accuracy better than real valued images. My question for you is that if you're gonna, I mean, it adds more parameters. For example, in your case, you showed that the number of parameters is double, but the accuracy is also 5% double. The training time is also kind of maybe doubled. So what if you just train with the amplitude itself? Because your results, what with amplitude, because you showed 5% difference between complex valued and real valued. You have got 5% almost more or less.
Yes, the real valued networks are trained with just amplitude. For example, for this one, the complex valued network trains with amplitude and phase, like the complex valued SLC data. But the real valued networks, since they cannot handle complex valued data, so they just is the typical way of doing it, like just using the amplitude.
So real value is just amplitude.
Yes.
So your both real and imaginary goes to your network, but if you just do with phase and amplitude, they are both real. Do you think that it will, because the real is just amplitude, but if you just use both amplitude and phase, because I have seen that some people also do that way, do you think that you get different result?
I haven't tested that for the classification, and I don't believe it would help a lot, because if you look at amplitude, the phase image from the SAR data, you don't see much information from for the classification. And the information that the complex valued network is getting is one part is due to the higher number of the parameters, and the secondly, it is the correlation between the amplitude and phase that it is exploiting. So it is not getting much information from the phase, just the phase itself. But for reconstruction, I tested, and for example, when we use amplitude and phase as the input in real valued network, and we reconstruct it, and we get two channels, the amplitude and phase, and then we get put them together to get the complex valued data. I'm sorry. This will not have the correlation between the amplitude and phase, so we cannot apply a lot of signal processing techniques. For example, SAW aperture. We can get SAW aperture images from it, but the SAW aperture images are very low quality, and it's not comparable with the input SAW data.
Okay. Did you apply any normalization when you were training? You just stick to your original values?
I need to think about it, because it was some years ago. But since it was deep learning networks, I believe I did. I'm not sure, but I believe I did apply some normalization using the mean and the mean and the standard deviation of the data, if I'm not mistaken.
Okay.
But I don't remember it. I need to double check it because
Yeah, no problem. Okay, that's totally fine. So you think that this is kind of applicable method for single complex images, but a lot of time you have dealt with the values, because the importance of the SAR is having both phase and amplitude with this complex valued network. Do you also consider the geometry of SAR in your network? Because the geometry is also, because a lot of time we just cannot use the computer vision based models for SAR, because SAR has its own special geometry. Do you think that it can matter as well here?
Well, I didn't apply any tests for that, but I believe to some extent it can be helpful with it, because that geometry, like there's a lot of information about the geometry in the phase and correlation between the amplitude and phase that we get. For example, the most prominent application, geometric application of SAR is INSAR, and it is using the correlation, the coherence between the phases. And since we have that in data, I believe it can be helpful, but I haven't tested it.
Okay.
So I cannot be sure about this.
Okay, that's totally fine. In the last part of your presentation, you showed some results about compression of your SAR data. Basically, a lot of time we don't know what we get from Sentinel-1, for example, Alaska facility. Do you know if they do the compression? Do they provide before compression or after? Maybe they do compression, but do you know which one do they apply on the data?
Well, yes, actually, that's a very good question, because we had problem with that too. Sentinel-1 uses FDBAQ, Flexible Dynamics Block Adaptive Quantization, FDBAQ, for compression of their data. And they do not be asked from ESA, but they do not provide the uncompressed SAR data because they don't have it. So in order, and because of that, the data that we have, like when you download the raw data, the level 0 data from Sentinel-1, it is already compressed, and you need to decompress it first to be able to use it. And it adds some compression artifacts to it, and it was affecting our data, because at the time we were doing this was a project that we did with DLR and Airbus. It was an ESA project, and DLR team had access to TerraSARX data, so they could test the method on TerraSARX data, and it was giving better results on TerraSARX because it was not compressed. They had uncompressed data, the original uncompressed data from TerraSARX. So what we did was, actually, I have it on appendix here. I didn't do much on this. It was most of the work from most of my colleagues, but we used this technique, which basically adds some random noise to the SAR raw data from Sentinel-1 to simulate the statistics of the SAR raw data, which is before the compression on the satellite. So the original SAR data that we don't have. But it's not the same, but it tries to match the statistics of the data from the original SAR data. So we applied this correction on the SAR data before doing the compressions that I showed. This was one of the pre-processing steps I did.
Okay, so you as I understood, you just simulated the data before compression by yourself, not you haven't had access to the original data.
Well, it's not a simulated data. It is the original level 0 data that you can download from Sentinel-1, but we added this pre-processing step to simulate the statistics of the data to match the same before that, applying the FDBAQ on the satellite.
Okay, very interesting.
Thank you.
So, I mean, this just to say, I mean, if you wanna apply the same technique on GRD data, these are just single complex data compression, right?
Yes. The data compression technique that I mentioned is for raw data, actually, not single loop complex. We tested for single loop complex as well, and it worked, but the results that I have here and the purpose of this model was to apply on raw data, not single complex, level 0 data.
Level 0, the signals, okay.
Yes, the signal because the application was to have this model instead of BAQ on the satellite to compress the data and send it to the ground station.
Okay.
So if we want to use it in as like in application, we will have the first encoder, the one in like the yellowish shade that I have on board the satellite. The red part, the red shade that I have will be the compressed data that will be transferred, and the green shade that I have here will be on the ground station to decompress the data.
Very interesting. I think now you can continue. If you have got any questions, please, you have almost half an hour. Any other questions? If you don't have, then Reza can continue, move on to the second part of his presentation. Yes, maybe Reza, you can now continue.
Yeah, thank you. And you can ask questions also later if you have any. Well, if I have time, before moving to those who didn't know about SAR and are not from SAR background, this is an illustration of how SAR Aperture works before I move on. And basically, this is the synthetic aperture of the SAR image that we get from, let's say, the single target that we have. And we virtually divide into 3 different SAR apertures, and we generate one image from each SAR aperture. So basically, intuitively, we can see that it is this image, the SAR aperture number 1 would be the image when we are looking from here and from the middle and from forward, looking at the back. So virtually creating 3 different views from one SAR image. Okay, now I will very briefly talk about what I'm doing here, which is not completely different, but it is a different application. It is a different work that I'm doing here in Edinburgh and NCO. And I'm working on process-guided concept bottleneck model and want to teach AI to think more like ecologists and scientists, how they think about the problem that they want to solve. And the problem that we want to solve is estimating above ground biomass, or AGB, from SAR data. Above ground biomass is all the living organisms on the Earth surface, above the soil. And it's mostly referred to the woody part of the trees. So when we want to measure AGB from forests, we want to measure the tree mass, the woody mass of the forest. It is a very critical metric that we need to measure. It is very important for carbon cycles and ecosystem dynamics in general, and carbon accounting, which is a big market. But it's not very easy to measure. The only direct way to measure AGB is to cut down the trees, dry them, and weigh the dry mass of the tree, which is, well, not feasible in large scale. We cannot cut down a lot of trees. So what ecologists usually do to estimate AGB is to go to these forest plots, to these forest inventory plots, and measure more easily measurable attributes of the trees, let's say canopy height, the diameter of the trees, and etc. And then use them in allometric scaling equations to estimate the AGB from them. Well, it is good for those locations, but it's again not feasible in global scale. We cannot go and measure all the trees on the planet. So Earth observation, especially SAR, is a very helpful tool for this to estimate the AGB globally. And SAR is the best tool for this from Earth observation data because it has a very good correlation with AGB. I'm showing one example here. With the AGB on the x-axis and intensity of the SAR data on the y-axis. But, well, this correlation is not very easy to understand all the time because this correlation, this relationship between them varies from site to site. It's different for each location. The the SAR backscattering tends to saturate in high biomass values, and also more important, especially for our field where we are working with deep learning, we need a lot of data. Grant of data for AGB is very scarce. It's very inconsistent from like just patchy locations on different locations and some information from LiDAR data. So it's not very easy to have a very homogeneous, very good behavior training data. So what we do here, you might be familiar with concept bottleneck models or CBMs. The idea behind CBMs, which is a model for increasing the interpretability and explainability of the learning models, is to define some human understandable at the bottleneck of the model and match the input data to these explainable and interpretable concept at the middle, and then match these concepts to the final output. And in this way, it is basically creating an intervention point and explainable point at the bottleneck of the model. We use the same concept and we extend it to process-guided CBMs or PGCBMs. And we want to teach the model to think the same way that ecologists think about AGB. So as I mentioned, the ecologist goes and measures different parameters of the trees and use allometric equations to estimate the AGB. So we want our model to first estimate different metrics, different parameters of the trees. Let's say the canopy height and number of the trees and etc. And then use these ones to aggregate and estimate the AGB. So we embed this process-guided knowledge into our model, and we force our model to go through this process in order to estimate AGB, instead of giving it the full flexibility to explore and find the best statistical correlation between the input and the output. And just to show some results, we have our results for some validation plots. Here we are showing on model estimated AGB on X and the field estimated AGB on the Y-axis. And our results are in green with overall bias of about 1.5 tons per hectare, which is considered better than the other models. We are comparing with the vanilla CBM, which is shown in red. Ours was process-guided CBM, and this is the vanilla CBM. We are comparing it also with the black box model. The black box model fits kind of better than vanilla CBM, but it is a well-known problem of vanilla CBMs that they increase the interpretability, but they usually decrease the performance. And we are also comparing it with two well-known biomass maps from ESA CCI biomass, which is the orange color, and the JEDI level 4B products, which again is a biomass estimation. In here, we are outperforming those one too. And as a final result that I'm going to show, there's one problem with a lot of these models is that they all have error, but this error isn't consistent in different structural attributes. So, for example, in here, we have the stem number density, the number of the tree stems that we have on the x-axis, and the estimation error, the absolute estimation error on the y-axis for different models. And in order to understand this structure-dependent bias, for example, JEDI has a very low bias on very low number of the trees when the biomass is low, when the number of the trees is low. The error for JEDI is also low, but the error increases as the number of the trees goes up. And all other models also fluctuate with different number of the trees, but PGCBM stays relatively flat, and it has some fluctuations, but it has a less structure-dependent bias. It has more stable estimation. And that was all I had to tell you about today. So if there's any question, I would be happy to answer.
Very interesting. Thank you very much, Reza. Do you have any questions? Okay, I have questions. For this new model that you developed, you have tried to embed more, ecological perspective as your input to your model, but I did not understand what type of data have you used and how did you consider this ecological modeling into your training?
Yes, well, I didn't explain it completely because well, I didn't want to focus focus of the presentation on this one. I just wanted to briefly mention it. But the input data that we use here, well, are allo star data, L-band. We are using ALOS data because L-band is has a higher penetration in canopy and it's better data for estimating the woody structure of the forest. And we are also using optical data as a proxy data, and for that one we are using the harmonized Landsat Sentinel-2 data for that one. And we are also using position data, longitude and latitude with sinusoidal position encoding to give the position understanding to the model as the input. We have different submodels in the concept submodels that I have here, and each of them predicts one attributes of the trees, the canopy height, the canopy cover, the number of the trees, or anything that we have the label for. We have some labels from JEDI, for example, canopy height and the canopy cover we can get from JEDI, which is a LiDAR, spaceborne LiDAR mission. And we have some of these labels from plot data that we have, these forest inventory plots. So, for example, number of the trees or the estimated AGB we have from the plots. So we have different models to estimate one of these attributes, like each of these attributes in here, and we first we pre-train each of these submodels separately with the respective label that they have. So we can use different sources for the labels. And then we have an aggregation module which takes these estimated attributes, which are still trainable, which are not fixed yet, and trains all of them as gets all of them as the input and trains to estimate the final AGB parameter that we have.
My question for you is that this the first box where you have concept models. So each of these neural networks, do you use each of these like Alice Pulsar and Landsat, or you combine them together? It seems that you use for each data you use one separate model.
For each of them, yes, for the data goes into each of them, but the same data goes to different branches to input to each of these ones. So each of them has a separate encoder, like encoder head. Like it's similar to multimodal models, which each modality of the data has a different tokenizer to harmonize the data for the rest of the model. For each of for these ones also we have a different, well, it's not a tokenizer but the encoder head for each of them to harmonize the input data so that it can be used in all the models.
Can you elaborate, because you showed in last slide that your model seems to give less dependent structure, less structure dependent bias compared to other models. So can you elaborate this in your model, model that you showed in previous slide? Why you get these results?
Well,
in terms of interpretation.
I have a very limited ecological knowledge. I'm not from ecological side. So, but from what we discussed here with the colleagues who are from more ecology side and with more ecological knowledge, is that, well, there isn't a lot of these models have these structure dependent bias. Is that, for example, if you have, let's say, 100 small trees, and you have, like, for example, for this one, you have 50 ton per hectare biomass. You can have the same amount of biomass with just maybe 2 or 3 larger trees. So there isn't a direct relation between the biomass and number of the trees. you can have like the same biomass with different number of the trees. But a lot of these models try to just match the trees that they are seeing there with the biomass and try to have like a maybe not a linear but a second degree correlation between the number of the trees or like different attributes that they are seeing and the biomass, which is not correct. But in this architecture, since number of trees is not the only information source, they have like different other like the canopy height, the canopy cover, the size of the trees, and also more importantly, because also allometric equations have these information in them, but they treat all of them as independent parameters. But in this one, we are accounting for the correlation between the causal correlation between these different parameters. And I believe this is the main reason that it's performing more stable for.
So my understanding is that a lot of time we train the models for different areas. Like for example, if you train your model in boreal forest, we train your model in tropical forest. Your model is not very general to different areas. When you want to try transfer learning, it will fail. But it seems that your model has addressed this problem and has seen different structures. Or maybe I'm not sure if you try to train it with different areas, then it should work better even.
Yes, well, the focus of this study up to now was Southern African dry tropical regions. So it was not very wide and it was not very generalizable. We haven't tested that. But theoretically, we can say that it is more generalizable than the CBM and the black box model because, well, if we consider the rhythmic complexity of the models, the black box model has the whole world to find the solution because it's not constrained at all. CBM model is constrained, so it is reducing the rhythmic complexity of them, of the models to have a smaller area to search for the optimal solution. So it is becoming more generalizable. And PGCBM, since it is putting even more constraint on this solution space that we have, it is further reducing the rhythmic complexity of the model. So theoretically, we can prove that it is more generalizable. But in practice, we are seeing some signs of it, but it needs more work. We have to, as I mentioned, we haven't tested in different regions. It has been just in one biome, Southern African dry tropics. So we need to test it in practice, but theoretically, we can be sure that it is more generalizable.
Very good, Reza. Thank you very much for your very excellent presentation and nice works.
Thank you. Thank you very much. I'm glad to be here and had the opportunity to present.
More great pleasure to meet you.
Thank you.
Any other questions? If not, then we just finish here and hope to see you again in other meetings.
Thank you. Thank you for inviting me. It was a pleasure to present and hope to meet you soon.
Thank you. Have a nice day all. And yes.
Yeah, thank you.
See you later. Bye.
Yeah, goodbye.
Recording here.